And I'm Louis Yang from Rutgers University. And today I'm going to talk about my paper, BigRoad, Scaling Road Data Acquisition for Dependable Self-Driving. And this is a joint work between Rutgers University's Stephenson Institute of Technology and Binghamton University. Self-driving offers an unprecedented opportunity to transform safety, efficiency, comfort, and economy of road travel. However, it is well recognized that ensuring dependability under very stringent conditions remains to be a key challenge. Developing dependable self-driving requires understanding of not just common highway or city traffic situations that has been addressed by a number of prototypes already, but also a plethora of other different and unusual events that are really rare to capture. Well, each such event may be rare, but in aggregate, they present a significant risk that the technology must address. The average human driver can handle such unusual events without fatalities for 100 million miles. To demonstrate the dependable performance at the human driver level, self-driving car require avoiding fatalities with those unusual events that might be encountered in billions of miles of driving. Most existing efforts to collect driving data build on small fleet of highly instrumented vehicles or reverse engineer the certain vehicle canvas. However, limited by the vehicle numbers, even if they're continuously operating on the road with test driver, it is still challenging to accumulate sufficient large data set in a short time period. So to address this issue, we introduced this BigRoad that can scale road data acquisition to a large number of commercial vehicles, so that we can easily achieve billion miles goal in a short time period. BigRoad aims to minimize the instrumentation of the vehicle by relying on smartphone and inertia sensor that can be affixed to the vehicle. Such setup can be easily deployed to a large number of vehicles and significantly accelerate the data acquisition speed. Here's the contribution of BigRoad. BigRoad can derive internal driver inputs, such as steering wheel angle, driving speed, vehicle acceleration, and external perceptions of road environment, such as road condition and front-view video. Most of this data are generated on the same smartphone, so they can share the same timestamp. We believe such synchronized data is extremely useful for training self-driving system and can be used to detect unusual situations that are useful for self-driving. Here are two key challenges towards large-scale data acquisition. First, how can we accurately determine proprietary driver inputs, such as the steering wheel operation, with such lightweight instrumentations? So the key challenge is that the steering wheel angle is proprietary data that are not available from the commercial OBD device, and the accuracy requirement for self-driving is really high. So it is really hard for us to accurately determine the steering wheel angle with some naive approach, such as using a camera or a smartphone mounted on the dashboard. So here we introduce a steering wheel angle estimation method that based on a smartphone and the inertia sensor, which we'll call it IMU in the later part on the steering wheel. So the reason we pick IMU is it can be used to track the steering wheel motion with a really low installation overhead. So the contribution here is we use the IMU to track the steering wheel angle and use the inertia measurement from the smartphone to real-time remove the error caused by the vehicle motion. So before I go to much detail, I will first introduce the steering wheel and coordinate system. So as you can see here, this coordinate system's the axis lies on the two-dimensional plane of the steering wheel, and its y-axis, as shown in the right figure, is perpendicular to this two-dimensional plane marking out of the steering wheel. So we assume that MU's sensor measurement can be read inside this steering wheel coordinate system at this point. So when the steering wheel is rotating, the steering wheel will rotate around its y-axis for a certain degree theta. So typically, there are two approaches to derive this angle change. First, we can use the gravity projected on the two axes, x and z, to derive this steering wheel angle, which we call it accelerometer-based approach. However, the accelerometer reading from the inertia sensor has large dynamic error, which will cause a large vibration at once. The second approach is based on the gyroscope reading. So we can accumulate the angular velocity on the y-axis of the steering wheel to get this steering wheel angle change. However, the integration process suffers from accumulating error, which will result in a large rate over time. To overcome these limitations, we use a complementary filter to fuse the result of the two approaches. We use a high-pass filter to fuse the gyroscope-based approach, and we put the accelerometer-based approach to a low-pass filter to feed this drift problem. And the parameters you see here, we use it to adjust the weight of two filters. However, we find that this accelerometer-based approach may not work very good inside the vehicle system. Because in the vehicle, besides the gravity, the vehicle's acceleration will also apply on this two-dimensional plane of the steering wheel. This acceleration will cause by vehicle turning, accelerating or braking. We empirically find that this acceleration may cause 10 to even 30-degree error when vehicle is turning. So method is needed to remove this error, say the error caused by the vehicle motion. Based on some mathematical deviation that we detail explain in our paper, we find that this data error can be calculated by only using the acceleration in the vehicle's coordinate system. And it is independent of the rotation of the steering wheel. So we use the accelerometer reading from the smartphone to calculate this data error and remove this from the accelerometer-based approach result. Here's the illustration of how this process benefits our system. So we show that the green curve is the error, is the estimated result before we apply this, remove this data error, and the blue curve is the result after we remove it. And compare them with the red curve, which is the ground truth, we show that the result significantly improved after we apply this motion remove algorithm. Here we come to the second challenge. How can we make the set of value deployable across different vehicle models? So in order to make the system value deployable in different, large number of vehicles, we need to make sure that the system can calibrate itself to different steering wheel positions, and also the different sensor placement on the steering wheel. So to solve this problem, we propose a device calibration method. So the challenge here is that most devices have their own coordinate system, and the sensor measurement need to be aligned to a fixed coordinate system before they're useful. So in this process, we first align the coordinate system of the two devices to the vehicle's coordinate system with our coordinate alignment. We introduced it in our previous work. And we also propose a new method to further align the end-use coordinate system to the steering wheel coordinate system we introduced in the previous slide. So here, give a vehicle's coordinate system and the steering wheel coordinate system inside. When the steering wheel is turning, based on the angular velocity projected on the y and z axis of the vehicle's coordinate system, we can calculate this phi pitch, which is the pitch angle of the steering wheel, and further align the mu from the vehicle's coordinate system to the steering wheel's coordinate system. So I need to know that with this mechanism, as long as the mu is mounted on the rotating part of the steering wheel, we can rotate its coordinate system to the steering wheel's coordinate system. So here are some other options from BigRoad. BigRoad uses the GPS accelerometer reading to derive high-frequency vehicle speed on smartphone. And here is the equation of how we use the complementary filter to fuse the result of the input of the GPS and the accelerometer. And BigRoad can also derive vehicle acceleration by directly reading the accelerometer reading from the smartphone after a line to the vehicle's coordinate system. And besides, we also propose a roll condition estimation method. So this method is different from previous approach that depend on additional setup near the tire or rely on cameras that is depending by the condition. We show that BigRoad can detect better roll condition using only the cross-out complex action force that are calculated using the inertial measurement from the smartphone. So to evaluate the accuracy of BigRoad, we conduct the experiment as follows. So we put the MU on the steering wheel and the smartphone on top of the dashboard. The whole experiment contains 6 vehicle models, 7 drivers, 143 daily compute drive in 3 months period, in various types of road conditions in New Jersey and New York State. And here's the lab demonstration of our system. We show that BigRoad can record front-view video, steering wheel angle, vehicle speed, and acceleration in real time. And the illustration also shows high consistency between the estimated result and real human operation. So to evaluate the accuracy of our system, to evaluate the accuracy of the steering wheel angle, we need to get the ground truth of the steering wheel angle. To get it, we use a special design OBD device provided by General Motors, and we also reverse engineered Honda Civic. By comparing our method with a baseline phone-based approach, we saw that BigRoad can accurately determine the steering wheel angle with mean error of 0.69 degree and net percentile error of 1.99 degree. With this error, it is even higher than some commercial steering wheel sensors that designed for e-vehicle uses. Some more detailed results can be found in our paper. And second, we showed that BigRoad's driving speed reading outperformed Android speed reading with a mean error of 0.65 km/h. And for the road condition, we showed that BigRoad can determine whether the road is dry or wet with 95% accuracy with using only 50 brakes. And we further want to know whether the data from BigRoad is useful for self-driving. So here, we push the data we collected into a deep neural network-based self-steering algorithm. So this algorithm takes the input of the prompt video and output the steering wheel angle for each frame. This algorithm contains 3 convolutional layers and 2 fully connected layers. And we push the data we collected from the vehicle canvas, which you can assume is the ground truth. And the data collected from BigRoad to this algorithm separate and generated 2 models. Here we use 2 models to predict the steering wheel angle for driving training. And we show that the model trained with BigRoad can achieve a similar performance compared to the one trained with the vehicle data, with a mean error of only 0.9 degrees. So here I'm going to conclude my work. So in this talk, I present BigRoad that can scale raw data acquisition to a large number of vehicles that can be used for self-driving. And we show that the driving and raw data can be estimated accurately using very few off-the-shelf sensing devices like the smartphone and the inertial sensor. And we also show that BigRoad can calibrate itself to different vehicle models and steering wheel positions and sensor placement. In the future, we plan to build an easy-to-install and sustainable setup for BigRoad so that we can really deploy it to a large number of vehicles and without much human operation and with a sufficient long lifetime. And second, we will design an interesting and unusual event detection method on the smartphone so that we can provide the data we collected another layer of information. And the final goal is to deploy the BigRoad system to a large number of vehicles and generate a useful data set for self-driving community. Thank you very much, and I'm here to take any questions.